So welcome to the second part of the lesson. So now what we do is to generalize the Euler-Lagrange equation for integral functionals to the Sobolev case. So before doing that, we do a quick recap of what we saw in the regular setting. So recall that we denoted by x the set of C1 functions on AB, such that u of a is equal to alpha and u of b is equal to beta. And C1 functions with Dirichlet boundary conditions. And then X was a reference, an affine space with reference vector space given by V, the space of C1 functions which are 0 at the boundary of the interval. And the Lagrangian, which is defined from AB times R into R, and denoted by we denote these three variables with the letters x, s, and psi respectively. And with this we can define the functional f on the space x, which is just the integral from a to b of L computed in x, u of x, and u dot of x, integrated with respect to the one-dimensional Lebesgue measure. And the first main theorem we saw for the Euler-Lagrange equation connected to this functional here was theorem 4.5, which I'm going to recall here. So suppose that the Lagrangian L is continuous and is C1 with respect to S and psi, so the two variables where basically you plug the unknown function u. Then we have 1 that if u0 minimizes f over x, then u0 solves the integral form of the Euler-Lagrange equation, which was given by this expression here. So it's the integral from a to b of partial derivative with respect to s of the Lagrangian, computed at u0 times v, plus partial derivative with respect to psi of the Lagrangian computed at u0 times v dot. And this is equal to 0, and it holds for all v in the test functions v. So meaning the C1 functions which are 0 at the boundary. If moreover we assume that L, the Lagrangian, is C2 and u0 belongs to x and is C2 additionally, and is also a minimizer for f over x, then we know that u0 solves the differential form of the Euler-Lagrange equation, which is the one here. So it's total derivative with respect to x of the Lagrangian derived with respect to psi computed at the point u0 equals to the partial derivative with respect to s of the Lagrangian computed at the point u0, and this holds for all points x in AB. So this is a classical ODE, remember, and it holds pointwise for all x in AB. And of course you have the boundary conditions, which are coming from the fact that u0 belongs to x. So here I should say u0, of course, to be precise, u0 and u0. Okay, the second result we're going to see is we're going to generalize is theorem 5.4, which talked about sufficient conditions for being a minimizer. So in this we proved that if the Lagrangian is C1 and u0 is a solution to the integral Euler-Lagrange equation above, so this one here, then we have that 1, if L is convex in with respect to the s and psi variables, then u0 is a minimizer for f. And 2, if L is strictly convex in s and psi, then u0 is the unique minimizer for f. So these two results are, say, complementary, because theorem 4.5 is talking about necessary conditions. So if you look at minimizers, then you know that minimizers solve, in general, the integral Euler-Lagrange equation, and if the Lagrangian is smoother, they solve the differential Euler-Lagrange equation. And instead, the second theorem talked about sufficient conditions for being a minimizer, which are solving the Euler-Lagrange equation and convexity of the Lagrangian. So, okay, we want to generalize these two results. We start with theorem 4.5. And the initial step is to relax the assumptions on the Lagrangian L, just by requiring measurability instead of continuity. More precisely, we require that L is a carotedory function, as defined here. So a carotedory function can be defined as follows. Let omega in Rd be an open set, and L, a function defined from omega times r to the power of n into r, where n here is generic and different from d a priori, so they can be different. So in this setting, we say that L is a carotedory function if the map y maps into L of xy is continuous for almost every x in omega, and if this map going from x into L xy is Lebesgue measurable for all y in Rn fixed. So, okay, a carotedory function is not continuous, but we're requiring that if you freeze this argument here, so if this is frozen, then the resulting function must be continuous, and this has to be true for almost every point in omega fixed. And second, we require that when the argument here is frozen, then the function is Lebesgue measurable, and this has to be true for all points here which are fixed. Usually we apply this in this setting. So in our setting, L is the Lagrangian, so it's defined from AB times R with these names here for the variables, as usual, x, s, and psi. And so when we say that this Lagrangian is caroteodory, we mean that you have to take omega equals to AB in this definition here. So this would be AB, this first set. And n instead, so d is equal to 1, sorry, in this case, and n is equal to 2. So this one would be r times r. And also the variable here in R2 is just the variable s psi. So basically we are requiring that the Lagrangian is, so that this function here so this has to be continuous for almost every x in AB, and instead the function that maps x into L of x, s, and psi has to be measurable for almost every s psi in R2 fixed. Okay. For example, consider this Lagrangian here from 0, 1 times r into r, defined as alpha x plus g of s and psi. Then obviously when I fix, for example, if I fix these two arguments, then this becomes a constant. And so I'm basically requiring that the map x that maps into alpha x is measurable. And likewise, if I freeze the variable x, then this is a constant. And so I have to require that this function here, s psi, maps into g of s psi. This has to be continuous for almost every x fixed. Okay, a proposition which we are not going to prove, but you can look at the proof in the proposition 3.7 in the book by Da Corogna. So the proposition is as follows. Let omega be open and L be a carotedory function, and also U be a measurable function, so that we can consider this composition here. So just for a sec, U maps from omega into Rn, so it's okay to evaluate U in X and you get a value in Rn, so this composition makes sense. And the proposition says that if L is Karateodori and U is measurable, then the resulting composition, which is a function from omega into R, is still measurable. And again, we don't make the proof, but it's very easy to do it by, since measurable functions can be approximated by step functions. So a density argument immediately shows that this is indeed measurable. But we are not interested in the proof. Okay, so weak Euler-Lagrange equation. As I was mentioning, we want to first generalize theorem 4.5, meaning that we want to, first of all, cast a minimization problem on Sobolev spaces for functionals in integral form. And then we want to derive necessary conditions for some U0 in the Sobolev space to be a minimizer. So we will see that U0 solves a form of Euler-Lagrange equation, which is very similar to the integral Euler-Lagrange equation we saw above. Okay, our setting is the following. P is always larger or equal than 1, and A is strictly less than B. And we consider the space X of functions U in W1P of AB, such that U of A is equal to alpha and U of B is equal to beta. So we're doing exactly the same as before, just earlier we had here, instead of W1P, we had C1 of AB. So now we're just relaxing the class of functions, but we're still enforcing the Dirichlet boundary conditions. So first of all, note that, let's underline this. Let's highlight. So first of all, note that X is well defined, since we already know that functions in W1P are continuous by theorem 7.19, and so it makes sense to evaluate U at points. And also notice that X is an affine space with reference vector space given by W1P0 of AB. And this is immediate to check because we know that functions in W1P0 are 0 at the boundary, as we just showed in theorem 7.34. Okay, so W1P0 plays the role of the space V, which usually is the C1 functions, C1AB, such that U of A equals to U of B equals to 0. In this case, V is just W1P0. Okay. So then we consider a Lagrangian and define the functional, the integral functional f from W1P AB into R just by integrating the Lagrangian on the function U. So f of U is the integral from A to B of L evaluated at x, U, I mean U of x, and then U dot of x. And notice that this is the weak derivative of the Sobolev function U. And also, this makes sense because, first of all, okay, W1P functions are continuous, so you can always evaluate U of x at any point in the domain AB. Instead, for the derivative, U dot, this is just an LP function of AB, so it doesn't really make sense to evaluate this function at points because this is a class of equivalence of functions, so you can just change U dot in a set of measure 0, and you're still okay. And you're still in the same class. However, remember that the Lebesgue integral doesn't see changes on sets of measure 0, so integrating U dot of x makes sense, because so this does not depend on the representative that we choose for U dot, as the integral will always be the same. Okay, so now we're ready to state the Sobolev version of theorem 4.5. Okay, the assumptions under which the theorem will hold are summarized here. Assumption 8.3. I thought that this was more convenient because they're rather long. So assume that L, Ls, and Lxi are Carathéodory functions. So this means that L is Carathéodory. It is differentiable with respect to S and differentiable with respect to Xi in the classical sense. And we're requiring that these two functions, so L, for example, Ls, which is defined from AB times R into R, and same for Lxi, we're requiring that these two functions are also Carathéodory functions. And then we suppose that either of these two conditions hold. And these are growth conditions on the Lagrangian. So the first condition, H1, says that for every R larger than 0, there exists an L1 function, which we call alpha 1, and an LP prime function, which we call alpha 2. And this P prime is the Holder conjugate of P. So this is P over P minus 1. So maybe it's better to write it here. So P prime is defined to be P over P minus 1. And beta, a constant which depends on R. So for every R, you must have these three guys here. So alpha 1, alpha 2, and beta. And then we require that for every X in AB, for every S smaller than R in absolute value, and for every Xi, these estimates hold. So the Lagrangian L and the derivative with respect to S must be bounded by alpha 1 of X times beta, plus beta times the P power of Xi, of the absolute value of Xi, and this has to be true again in this for these values of X, S, and Xi. And instead we require a different growth condition on Lxi, which has to be bounded by alpha 2 plus beta Xi to the power of P minus 1. Instead, the second assumption, which is stronger, actually, I think, yeah, it is stronger than H1. Then we require that for every R greater than 0, there exists alpha 1 in L1 and beta, a constant, such that, again, for the same values, so X in AB, S in absolute value less than R, and Xi in R, we require that all three of these guys, so L, its derivative with respect to S and its derivative with respect to Xi, are bounded by alpha 1x plus beta Xi to the power of P. Okay, so given this set of assumptions, we have this theorem, theorem 8.4, which states as follows. So suppose that assumption 8.3 holds, and let U0 in X be a minimizer for F over X. Then we have 1, that if H1 holds, then U0 satisfies the weak form of the Euler-Lagrange equation, which is this one. So the integral from A to B of the S derivative evaluated at the point U0 times V plus the Xi derivative at the point U0 evaluated at V dot has to be 0 for every V in W1P0 of AB. Okay, so remember in the regular case, you were testing against functions which were C1 of AB and 0 at the boundary, or rather yes, exactly those. And instead here you can just test against Sobolev functions, which are 0 at the boundary. And we call this weak Euler-Lagrange equation. Number 2, if instead H2 holds, then U0 satisfies the even weaker form of the Euler-Lagrange equation, which is basically the same equation as above. So this one and this one are exactly the same equation, but you test against less test functions. So this has to hold, this one here, has to hold for every v in C infinity compact of AB, whereas this one was holding for all functions in W1P0. And this is weaker, obviously, because C infinity C is contained in W1P0 strictly, actually. And so you see that the weaker form of the Euler-Lagrange equation requires way less test functions, so it holds much less in general than the red one, the first one in point 1. And 3, I mean, so these 2 points are the novelties, let's say, with respect to the old regular case. And instead you'll see now that point 3 obviously is the same as before, because it just says that if in addition L, so the Lagrangian is C2, and U0 is actually regular, so it's also C2, then U0 satisfies the classical Euler-Lagrange equation. So this is the same as for the regular case. But again, this is still a novelty in a way, because here a priori we're just defining the functional on the W1P functions and not on C1. So here there is actually something to prove. Okay, let's look at the proof of this theorem. So the first step is that we need to show that f is, so the functional is well defined, because this is not actually trivial, since we're assuming very low regularity on the Lagrangian and on the ambient space. So okay, let U in W1P of AB. Then both, by definition, we know that both U and U dot are LP functions, so they are both measurable by definition. And we're also assuming that L is Karateodori. And therefore, by proposition 8.2, the one we just saw about measurability, we get that the function defined from AB into R by g of x, g of x is said to be L, computed at x, u of x, and u dot of x. We know that this function here is measurable. So this is the function appearing in the definition of f, because so f of u in this case is just the integral from a to b of g of x in dx. And since this function here, g, is measurable, then we know it makes sense to compute its integral. And I mean, it makes sense to compute the Lebesgue integral, but of course, a priori, the integral could be even plus infinity or minus infinity. But it doesn't matter, we still say that the function is integrable, right? So as long as the function here is measurable, you can actually try and compute an integral. It doesn't matter if the value is plus infinity or less infinity. Okay, so therefore g can be integrated with the integral possibly being unbounded. Next, we want to show clearly that f is bounded for every u in W1P. And here is where we use the assumptions. Okay, since we know that W1P is embedded in L infinity, and this was true by theorem 7.27, we get that U is in L infinity, and therefore we have the very trivial estimate that the absolute value of U and at a point x is less or equal than the L infinity norm of U, almost everywhere in AB. And therefore, if we choose R to be this L infinity norm in the assumptions H1 or H2, so just to go back to these assumptions here. So you see that both assumptions H1 and H2 said that for every R there exists a set of either two functions and a constant, or one function and one constant, such that these estimates hold for all values here. But notice that S is squeezed in a box, so S can only be in some interval around the origin. So this is r and this is minus r. And notice that s is the variable where we plug u. So it makes sense that I mean we want an estimate basically to hold for all values. We want to estimate this guy, right? U of x, u dot of x in absolute value. So basically to use this either of these two estimates here, h1 or h2, you have to make sure that for every x in AB, the point x, u of x, and u dot of x lies inside this set here, basically. And so you see that for the point x you have no problem because it's always in AB, and also for u dot it can be whatever because these estimates are assumed to hold for every xi in R. But so the only point where you need to be careful is for u of x, which needs to be bounded by the constant R. And so we just take the worst possible value for this one, which is just the L infinity norm of u. Okay, again, because u is Sobolev and therefore is L infinity by the Sobolev embedding. Okay, I wanted to clarify this point because obviously we will use it constantly in this proof because all we have are assumptions h1 and h2, and so you're always required to squeeze the variable s inside some interval. Okay, so choosing this value of r in h1 or h2, we know that there exists alpha 1 in L1 of AB and beta, a constant depending on r, such that L is less or equal in absolute value of alpha 1 of x plus beta absolute value of xi to the power of p for all of these values. Okay, for all x in AB, absolute value of s less or equal than u infinity, and xi in R. And notice that this guy here always belongs to this set for what I was saying before. Therefore, you can always apply this estimate when you evaluate L at the point of interest, which is x, u of x, and u dot of x. And we get this condition here. So the absolute value of f, we just pass inside the integral the absolute value. And then since this point satisfies this condition, which again is this condition here, you can just apply this estimate and obtain that this is less or equal than the integral from a to b of alpha 1 plus beta, the integral of u dot to the power of p. And this is less than plus infinity because alpha 1 is required to be in L1 of AB, and here we're integrating it from a to b. And this is a constant, and here you get xi to the power of p, meaning you have to plug u dot here, and this is finite because u belongs to w1p, and therefore u dot belongs to LP, and therefore f is finite and well defined. Okay, because remember so the strategy to obtain the Euler equation, the Euler-Lagrange equation, was to given a functional f to compute the first variation, and if so the first variation which we denoted by delta f, and if u0 was a minimizer, then we knew that that this was 0 for all v in the affine so v, this v is the reference vector space for the affine space v x, so u0x minimizer. And this is what gives us the Euler-Lagrange equation. So the idea is to do the same now, and we know that in affine space this guy is just the Gateau derivative. So let's see if I mean, it's not a surprise, but this functional f is Gateau differentiable, and so we just need to compute the Gateau derivative. Okay, let's do that. First of all, we need to Okay, the claim is that f is Gateau differentiable at every u in W1P and in every direction v in W1P. So, okay, we can just disregard boundary conditions, and it is true that f is just differentiable on the whole space in every direction. So, okay, the difference quotient for x writes is this one. So remember that for computing the Gateau derivative, we need to compute this limit. So, which is just the variation of f at u in direction v. And we claim that double star holds, so that this limit is equal to this integral here. So ls evaluated at the point u, so this is the point where we are differentiating, times v, which is the direction, plus xi evaluated at the point u times v dot. And clearly this is, as you can notice, this is the guy that will be 0 in the Euler-Lagrange equation. So we will have this equals to 0 for every v in an appropriate class, for minimizers, of course. Okay, so we need to show double star. First of all, notice that since we are assuming that ls and xi are Karateodori, this means that these two maps are continuous for almost every x fixed. So this is the definition of Karateodori function. And therefore we can apply the standard chain rule to conclude that this map here is differentiable, because so this is a map sending t into the variation. So x here is fixed, and so you just need to differentiate L with respect to these two arguments here, and you know that L is differentiable with respect to these two arguments by assumptions, because you know that we assume that these two are continuous. Okay. And the derivative you can immediately compute. I mean, this is the classical derivation of a composition. So the derivative with respect to t of this function here is just so the derivative of this argument with respect to t, which is just epsilon times v, times the derivative with respect to s of the function evaluated at this point, so this one, and then the same for the second argument. So the derivative of this one with respect to t is epsilon times v dot, which are here, times xi evaluated at the same argument here. Okay, now it is convenient to introduce some notation, because obviously we have to carry around all this stuff. So we define g of x comma epsilon to be the function defined like this. So it is the integral from 0 to 1 with respect to t of this guy here, basically. Divided by epsilon. Okay, so the integral of this guy. And we notice that now we want to explicitly write the difference quotient for f. So 1 over epsilon times f evaluated at u plus tv minus f of u. This by definition of f is equal to this guy here. So maybe let's put a parenthesis here to be more clear. Okay. And by the fundamental theorem of calculus, so this is the trick that we're going to use, since this is differentiable with respect to t, you know that you can just write this as the integral from 0 to 1 of the derivative with respect to t of this function here. And you can immediately check that this guy here is equal exactly to this guy here. Okay, because t is ranging from 0 to 1. So this function evaluated at 1 is equal to basically to this one here, which I'm underlining. This one here. And for t equals to 0, you get this function here. Okay. And by triple star and the definition of g, what was triple star? Yeah, triple star was the pointwise derivative. with respect to time. So we can just explicit this derivative and then recall the definition of g to notice that the first variation can be written as the integral from a to b of g x epsilon evaluated at x. And so now we need to compute the limit as as epsilon that goes to 0 of this integral. So here you have a measurable function, and you want to pass to the limit under the sign of integration, and so we need to use Lebesgue dominated convergence, clearly, or one of the theorems on exchanging the limit and the integral. Okay, so this is, I'm just rephrasing 2 star, because, so this was the difference quotient, and this is what we want to show, that the difference quotient was equal to this guy here. And just notice that this function here is just g evaluated at x and 0 by the definition of g, because let's go back. G was defined like this. So if you set epsilon equals to 0 here, so this goes away, and also this goes away, and this goes away. So with t as well. So you notice that basically you get something which does not depend on t. So you can just take this constant here. So this is constant with respect to t. You can just take it outside of the integral, and the integral from 0 to 1 of 1 in dt is equal to 1. So g of x 0 is equal exactly to this guy here. Okay, so this is the claim we need to show for for Gateau differentiability. And the idea is that okay, fine. So now I'm just noticing that I'm using maybe I'm using the same label here, but they're different. Okay, but that's fine. So to show C, we use dominated convergence, because we need to show, first of all, that, and so we need to show A, that g of x epsilon converges to g of x 0 for almost every x in AB. And second, we need to show that this is bounded by an L1 function of AB for every epsilon. Okay. So these are the two assumptions of the Lebesgue dominated convergence theorem. To do that, we first notice that that by this, so okay, what's the idea? Obviously, we want to use H1 in this case, and so we need to be sure, like before, that the argument with respect to, so this argument here, because g of x epsilon was this guy, so we need to make sure, of course, that these two are squeezed in a box, because this is the argument with respect to this is the S argument, which needs to be bounded for our assumptions. So we just need this function to be bounded, but we're in luck because we're assuming that both U and V belong to W1P, which we know is embedded into L infinity. So obviously we will be able to choose R in a way that this function here in absolute value is always less or equal than R. And so we can apply the estimate H1. Okay, so let's move forward with the proof. And we start by showing the pointwise limit in point A. First of all, let's recall the assumptions. By the embedding W1P into L infinity, you have that U plus epsilon TV belongs to L infinity for all epsilon greater than 0 and T in 0, 1 fixed. And in particular for epsilon between 0 and 1, because we're interested in small values of epsilon, we have to take a limit as epsilon goes to 0. And for all values of t between 0 and 1, we get that u of x plus epsilon t v of x in absolute value is less or equal than the norm of u in L infinity plus the norm of v in L infinity. And this is true almost everywhere on AB. Therefore, we can just choose R to be this constant here. So the sum of the two norms. R is the constant in H1. And so we obtain the existence of alpha 1 in L1, alpha 2 in LP prime, and a constant beta, such that these three estimates hold. So this is just the assumption H1. Okay, and these three hold for all these values here. So for any x, nxi, and any s, which is between minus r and r. Okay. To show A, the pointwise convergence, we need dominated convergence because gx epsilon is itself defined as an integral. So we already know that the maps here are continuous because ls and nxi are Kara-Theodori, and so they're continuous when you freeze the argument x and you look at them as functions of s and xi. Therefore, so this guy is the one inside the definition of gx epsilon. You see that you can just take the limit as epsilon that goes to 0 of this guy here, and by continuity you obtain this one. Because all these terms just, the terms involving epsilon obviously just disappear. So we end up with this term. And this is true for all t in 0, 1 and for almost every x in 0, 1. Furthermore, because u plus t epsilon b satisfies b, which is this bound here, then we can apply these three estimates to the point x, u, and u dot. And so, in particular, we apply estimate number 2, the one on the s derivative of L, to obtain that this guy here, which is this one. This can be immediately estimated as by 2. We know that we can estimate this with alpha 1 of x plus the constant beta times xi to the power of p, and xi in this case is this guy here. So you get this one, and times the absolute value of v, which is still here. Now remember that epsilon and t are between 0 and 1, so we can just throw these two away. And also we can apply this simple estimate here, which says that a plus b to the power of p is less or equal than 2 to the p minus 1 times a to the power of p plus b to the power of p. And this estimate holds for all p larger or equal than 1. And so we can apply to basically to u dot and plus v dot to the power of p, and we obtain this one here. So we can estimate this one by this quantity here. Okay, and always times v. And now we notice that the right hand side, so this whole function here, belongs to L1 of 0, 1 with respect to t. Because x is fixed, and basically this is a constant. I mean, there is no t involved, so it does belong to L1 being a constant. Okay, so now we estimated this first term, and we showed that it can be bound by an L1 function of t. Now we need to estimate this second term here, and this second term can be bounded by using the estimate tree, and similarly to what we did here, you can immediately obtain that Lxi evaluated at this point times v dot is less or equal than c of x, which is just a constant depending on x, which resembles this one, and obviously it belongs to L1 of 0, 1 because it is a constant. Therefore, we can just apply dominated convergence because we saw that this guy here converges pointwise to this one, and also this is bounded in L1 of 0, 1. Therefore, by dominated convergence, we can pass this epsilon under the sign of integration and obtain that the limit as epsilon that goes to 0 of gx epsilon is equal to this one, which is just g of x 0. And this shows A. Okay, now we pass to show B. Let me check the time. Okay, I think it's impossible to conclude this proof within this lesson. So next time we resume straight away from point B, and we conclude the proof. So okay, see you next week.